The following program is brought to you by Caltech.
Okay, so what we had after the Planck data, we suddenly realized that we need to explain theoretically models which lead to very, very low R. When we got bicep data, we suddenly realized that we need to go back to the models with sufficiently large R. And there's a totally different models. Then we have another purpose. We want to do it in a sufficiently good theories which would well satisfy theorists. And that is something which we are working. And I find it extremely interesting time. But before we're going anywhere towards realistic models, I would like just to make a bridge between, well, experimentalists, particle physicists, journalists, and everybody. Because when, for example, bicep data were announced, I received many questions from journalists saying, and what will it tell us about grand unified theories? And I told them, well, about nothing. And they say, what do you mean by that? And I ask, what do you mean by a question? So there is a real disconnect between those who really do particle physics, those who write books about particle physics, those who write, well, anything else about, well, inflationary theory. So first of all, some definitions. According to almost all college textbooks, inflation is an intermediate stage between the hot Big Bang explosion and a subsequent slow expansion of the universe. Intermediate stage, I emphasize it. It's an exponential expansion in the false vacuum state formed during the cosmological phase transitions with supercooling. And this phase transition lead to symmetry breaking between strong and electromagnetic interactions. Okay, so that's the standard lore. And now progress in development of, well, realistic versions of models of inflation occurred only after all of these assumptions have been abandoned. And somehow it just did not penetrate into consciousness of general public. It was done 30 years ago. For 30 years, everything that we are doing is incorrectly presented to general public. And each time when I'm giving lectures on inflationary cosmology, each time I'm telling my students, please don't read the book. That's a shame. That should be changed. Okay, so now after all of these emotions, let's talk about something which started the new generation of inflationary models. We are not sure whether it will finish it, but let's start with the beginning and then let's see what happened during last year, which brought to our attention quite a lot of different inflationary models. So that's a basic, simplest inflationary model with just a quadratic potential. That's from the point of view of simplicity. You can't go any simpler than that. But then Planck data released, and then what we see is that this is somewhere here, which is not a nice place to be. And the earlier cuisines like 5 to the 4th are somewhere out of the map. And now these are the base candidates. These 2 points are actually, these are Axion monodromy models, which Ivo will be talking about, and they have recent developments in changing and, well, modifying the predictions. Here is these orange points. They belong simultaneously, and that's already an interesting story, simultaneously to 2 different theories. One of them is Starobinsky model, which for a long time was not even considered by some as an inflationary model. And then suddenly it became a focal point of the Planck data. Now this is Higgs inflation model. These 2 models have the same experimental predictions, and they are just in the sweet spot of a Planck Planck data. So what we want to understand, what is that? Is it kind of mysterious coincidence that these models appeared at the center, or maybe there's something else is going on? This is, again, I'm just, well, previewing, well, not previewing, but making additional advertisement to the person who does not need any advertisement, and also to Liam. And this is what we are going to do. This is based on the series of papers by Renata Kalish, myself, and several other people we were trying to approach it from the point of view of supergravity. Because if you just want to draw a line, want to draw any potential, you can freely do it. Nobody prevents you from choosing your own potential and then fit whatever data you want. But if we restrict ourselves to, say, theories which are supersymmetric, once you say supersymmetric, then you say supergravity, because we are working in gravity, and supersymmetry plus supergravity brings you to supergravity. Suddenly, when you start working, you immediately have a problem, because in the simplest version of that, if you write down the F-term potential, you will have terms like that if your Keller potential is simplest. Okay, so once you do this, you have exponentially steep potentials and very, very difficult to implement any kind of inflationary models. Not only chaotic inflation, not even large field inflation, but with the small field inflation, you have some problems. So how do we do with that? And the suggestion to deal with that was proposed well, relatively recently. It was in 2000, some group of people from Japan, mostly it was a group by Yanagida. They proposed to take one of these Keller potentials having flat direction in the Keller, and then everything changed. This Keller gives you the same minimal kinetic terms as the previous Keller, but it does not depend, this one does not depend on the real part. Or you can change it, make it plus, and it will not depend on imaginary part. And in whatever direction you do not have any dependence, the previous dangerous term does not depend on this field, and therefore the main danger which will paused us from implementing inflation in supergravity suddenly disappeared. Now, in particular, if you take the simplest superpotential here, just, well, here you see two fields. One of them multiplied by another coefficient, and you get m squared phi squared. And if you take this model, look at the potential along this inflationary direction, check what happened in perpendicular direction. Maybe you would be afraid that you have some masses exponentially growing because of this other perpendicular direction. No, masses do not exponentially grow. If you calculate one loop corrections to this potential, no corrections up to the Planckian density, which would change the conclusions. So that's pretty interesting that you take the simplest potential, you're already doing pretty well. Now, what we did relatively recently with Renata and our student Thomas Rube, we considered this similar class of models, but more general. You have this superpotential of this type, generic. Then you have Keller potential, which can be much more general. You do not need it to be quadratic. You can take it logarithmic. The only condition is that it must be, well, flat direction of the Keller. In some direction, it should not depend on the field phi, or it should not strongly depend on this field phi. I will return to this later. And then for all of this class, independently of the Keller, you have potential of the inflaton field, which is given by what? By square of arbitrarily real holomorphic function, which you can choose whatever way you want, and suddenly you have a huge family of inflationary possibilities. So you have with this potential where functional freedom in choosing inflationary potential in supergravity, not just in every theory, but in supergravity, so with all restrictions, and therefore you can fit any set of NS and R, you just choose for them these functions which have proper derivatives in the proper places. You can fit all experimental data in front using supergravity. But then, of course, you would say, oh, well, this may be too much freedom. So see what happened. There was no freedom whatsoever. We could not do anything. And then suddenly we have too much freedom. So now we are going back and trying to see, can we do something elegant with them? Not only freedom, but also something nice, something generic, so that we can learn something useful using these models. So this is a simple example. You take this superpotential and you get your quadratic potential here. Well, no news. This was done in 2000 by Yanagida and company. Now look at that. This is the superpotential. We make a minor change. We just multiply it by 1 minus small factor multiplied by the scalar field phi. A very, very tiny change in the superpotential. Look what happens. When you take a square of it, you will obtain phi squared multiplied by the square of this thing. And then if you make a change of variables, just shift it by, well, half of this argument, you will find that this is exactly like Higgs model, spontaneous symmetry breaking. By tiny modification of your superpotential, you get model of this type. This is how it looks. And the smaller is correction, the larger the value of spontaneous symmetry breaking here. Now then you have two different inflationary regimes, falling from here or falling from here. Depending on where you're falling from, you have different predictions. If you're falling from large field phi, you are in this region, good for bicep. If you're falling from small phi, you're in this region, good for comparison with Planck. And by the way, what is this one? This is natural inflation, this pinky one. We will return to natural inflation later. You make a second step and you modify it just a little bit more, add a little bit more of this correction, and then you start bending the shape of the potential in whatever way you want, and then you plot the corresponding results. And depending on various parameters here, you can be in this area as low as you want, or you can travel here towards m squared, phi squared, or you can travel even higher, well, and doing it for bicep 2. So what I'm showing right now, that you take a basic model, you modify it just a little bit, you have enormous amount of freedom of changing your results. And this goes back to something which I would be unable to explain right now, but what is going on is that we are going to supergravity, but in fact we're going one step before it. Supergravity usually is formulated using superconformal approach. In the superconformal approach, it will be very important for me in the following. Superconformal approach, you do not start with a theory where the Planck mass is already fixed. You introduce some interaction with scalar field, and then you fix one of them, which is called conformal compensator. After you do it, you have Planck mass. But you start originally with non-minimal interaction with gravity. Okay? So it happens that in some models, when you formulate in a normal way, this e to the Kähler appears as a consequences of this non-minimal coupling to gravity. So when we are checking whether there are some corrections like that in front of F term or not, this may tell us something about non-minimal coupling to gravity in the basis of supergravity models used for inflation. So that's an interesting connection. And now if you add this non-minimal coupling there, then suddenly you have strongly rising up potential at very large values of the phi. And if it strongly rises, the meaning of what is going on is the following. Large distances, which means large phi, correspond to large distances. Their potential is very steep. Field phi rolls down very quickly. When it rolls down very quickly, amplitude of fluctuations, delta rho over rho, is small there. Then it rolls down to the place where it starts slowing down, amplitude rises. You want to have all of these, I don't, but anybody wants to have this ns depending on momentum, very easy to do so. And very easy to, very easy. It's possible to control this amplitude here. This red line is what you achieve moving it down if you play with the potentials like that. It's possible to do so without modifying or actually improving a little bit what is happening here near this peak and not touching anything that happens here and producing R of the order of 0.1. So it's possible to do so. Do we like it? Would you prefer to have something simple? Well, if you consider a standard model of elementary particles, we are right now in cosmology, hopefully, approaching the normal period of development of science where you do not have just philosophy, you have experimental data, you have many, many experimental points. When you have many experimental points, we need to have many possibilities to fix the, how many parameters, free parameters do we have in a standard model? About 20, just to fix everything that we know. How many do we have in minimal supersymmetric model? people stop counting, so it's about 200 or so. So we are doing all of this with 2-3 parameters in the model. So I think that it's okay, but we want to do better. We want to be natural, we want to be generic, so let's see what we can do. Yeah?
When you do that calculation, do you start with the field at rest at the top, or does it not matter how you
Well, if you are in the slow roll regime, then the regime when you go to the slow to asymptotic regime, it's just 1 or 2 e-foldings, so it really does not matter. Yeah, but these attempts to go steep at large values of field phi, they go back to the time which I would prefer even not to remember, because there was some time where we were pressed, say, but people who were saying that omega is equal to 0.3, okay? And you die if you do not, well, give us a theory which explains omega equal to 0.3. And eventually, we were pretty ready to die because all attempts to do this did not produce anything sensible. And this is the only model out of all of previous attempts which survived some kind, well, kind of survived, because it's an ugly model. And I can tell that it's an ugly model because I invented it. So it's an ugly model, but it has a feature. If you have something, but the models like that right now are used in this discussion of landscape, where you assume that last well, stage of inflation is short and it's achieved by tunneling, whatever. So after exhaustive studying of tunneling, which would produce something like that, this model, what happens is that when you are tunneling, you tunnel to the very steep fraction of the potential, and then you drop like a stone here. And as a result of that, perturbations produced at that time are strongly suppressed. So you just, if you want to have something like many people, like Linde, Susskind, and other, will say about the inflation in string theory landscape, we may return to the ideas like that. And the suppression of large L is not such a, of small L is not such an unnatural feature of these models. This is what happens when you take standard, well, okay, simplest model m squared phi squared, you modify it just a notch by adding this non-minimal coupling. If this non-minimal coupling is having constant psi smaller than 0 at the level of 10 to the minus 2, 10 to the minus 3, you are here. If it is positive, then you are here. So it shows you that when you start with something very, very simple, it is a huge sensitivity, at least to change of some of the parameters. We just want to do something which would not be so sensitive. But this is what we have right now. So depending on the cross purposes, if you're an experimentalist wanted to feed their data, is it Planck or is it, well, bicep 2, we can provide you with everything you want, except for we want to provide you something nice. So this was considered to be a nice idea. Natural inflation, naturally flat direction, sinusoidal potential in the theory of Axion type. Interestingly, this theory was proposed by Fries et al. In 1990, so it was nearly 25 years ago. Until now, there was no supersymmetric version of this model. All attempts to do it supersymmetric always lead to some instability with respect to some of the moduli fields. So this is what we did right now, just being stimulated by all of this rush with experimental data. We looked at it, we have found a way to find this well, sinusoidal potential, which is stabilized in all directions except for the necessary one, for the inflaton direction. And we have actually found dozens of different superpotentials which lead to the same story. So this is one of them, which looks like, well, one of the field, and this is like KKLT potential in string theory. But this, of course, is not a stringy theory because you have something else here. And that is scalar potential, but we are not obliged to have this t plus t squared. We can do it logarithmic. So many different versions, and you have what you have, and here is your cosine potential, which people were trying to achieve in this theory. And now this is a fun story. If you take two exponents, like in, well, racetrack potentials here, and then if you have a ratio of A to B irrational, which was long time ago proposed by, well, Banks and Dine and Seiberg. What happens here, we have right now supergravity generalization of this model, and when we draw the potential, it looks like a potential which have infinitely large number of different de Sitter vacua with different positive in these contents, different de Sitter values, and near each of these minima, you can have inflation. These are actually very soft potentials, and you have infinite number of possible predictions there. Oh no, do I say infinite number? If you have here a very large period, then near each of these minima, you have nearly quadratic potential, and then phi squared is a good theory to explain or to predict whatever happens there. Okay, so pretty weird stuff. This is something which you do if you add, the sinusoidal potential to any power law potential, and you have potential which is modulated by that. This is something which you take, you see, this is one field, and you have two constants which are large. Usually when you have large constant, people do not have inflation in natural inflation scenario. And if they have, then they need to add two different fields, and there will be cancellation between two different constants for two different fields. Now we have one field, and there is a cancellation of these two different constants for one field, and we have potential which is very, very, well, long wave, and you can have inflation there within the theory of one field. So it's lots of information which we are getting right now. See how excited we are because we were pressed to the wall and say, we kill you if you do not explain us everything, and everything changes every day. Okay, so here is two-field natural inflation. Beautiful. You just have these two sinusoidal waves. Okay, so easy. Now, models describe are good to explain large R, but good for bicep, but so they can describe small r. I have shown you this natural inflation going to small r. I have shown you this Higgs model going to the small r, but it's kind of tense. So let's try to see whether we can do something which would be in peace with Planck. And then maybe, actually, we can be in peace with both. You will see how it is possible. So here, yeah. Okay, so these are these points. It is corresponding to n equals 60, n equals 50 for Starobinsky model, and simultaneously for Higgs inflation. So what is the miracle? What is the reason? All of them predict 1 minus ns is 2 divided by n, where n is, well, a number of foldings, like 60. And r is given by that. So what is the reason? They are absolutely different theories. It's kind of miracle. Two absolutely different theories give you the same prediction. So it looks like either somebody give, yeah, I remember how it was with Wigner, who said that mathematics is a gift given to us which we do not understand and don't deserve. So there is something which we do not understand. Let's try to understand, because otherwise we will not deserve it. This is Starobinsky model. Okay, Starobinsky model originally, it was a mess of different terms. It was supposed to be based on conformal anomaly in gravity. It was really, really hard to look at it. Okay, and then it was based on the assumptions that originally our universe was totally, absolutely uniform and homogeneous, which goes against the logic of inflation, which tries to explain why it's uniform and homogeneous. Then 3 years later, the model was modified and it brought to this level, and it was, well, started being presented like a model which ideologically is similar to chaotic inflation, because previously it was assumption that you start in de Sitter space, and de Sitter space is unstable, but this is initial state, and then it was not quite clear how initial state can be unstable and still exist for infinitely long time before, well, inflation starts. So it was a problem with initial conditions. But in the theory like that, you can achieve it like using chaotic inflation. It was rewritten by Witt in the form which is equivalent to the theory of scalar field with this potential. And look at that. If you are here You're rolling here. This is chaotic inflation starting with this exponentially flat potential. And now you're going to see this exponentially flat potential several times during the remaining part of the talk. This is Higgs inflation. Higgs inflation with spontaneous symmetry breaking here. It, depending on the value of phi, if you take this psi here, if you take this psi large, then you are coming to the same point as Starobinsky model. And what is going on here is that you write down your potential here, you go with a non-minimal coupling to gravity, and you go to the Einstein frame. In the Einstein frame, your potential is given by a Jordan frame potential divided by something, and there is a relation between the original variables and the canonically normalized variables for the Einstein frame theory. And once you do that, the theory starts looking exactly like Starobinsky model. After you first go from Starobinsky model, R plus R squared, you massage it in the scalar field theory. Then you go to this model and you go from Jordan frame to Einstein. They look very similar. They are not equal to each other. This one for the Higgs model is symmetric with respect to going in this way. Starobinsky model is asymmetric, but the part of it looks similar, and their results are identical. Now, this is what was done in our paper with Rost, just a few months ago. We considered generic non-minimal interaction, like R multiplied by square root of V. Like if you have phi to the fourth, it will be R phi squared as usual. But we decided, okay, let's try. Okay, put here any non-minimal interaction of this type, and put the potential here. What happens? You have the same kind of theory. So we have much more generality than we expected before. And when we understood this, we actually understood that you can change this part as well and change this part as well. And under quite a lot of strong changes here, you will still have essentially the same potentials asymptotically in the places where it matters for prediction. So these predictions become very stable. And then we took these models and we decided to look at in the limit of large, if you have minimal coupling to gravity, this is the theory phi to the fourth. It's a straight line linking it to this Higgs inflation prediction. If you take the theory phi to the sixth, just forgotten long, and nobody even started doing anything like that, you go to the limit of large psi, it gives you the same prediction. Phi squared gives you the same prediction. So you have kind of comp of different possibilities, which all go through the area occupied by this Planck data. You want to explain anything like that, just in the context of the theories which we can use and explain that. Now, this is something else, totally different story. This was originally based on a different kind of supergravity theory, which was based on not on the chiral multiplets, but on vector or tensor multiplets. And there you do not need any other perpendicular fields to stabilize. And there we have found that it's a possibility to introduce a not only Starobinsky type of model, but its generalization characterized by some arbitrary parameter alpha. Nothing depends on beta. Nothing depends on this coefficient. Many things depend on this alpha. And in particular, n will be in this model is the same, but r is proportional to alpha. So if you change alpha, you change the predictions of the model. I will tell you later what is the interpretation of this parameter, but right now, just watch it. If alpha is small, then you can go even further below. If alpha is large, interestingly, if alpha is large, what happens is that inflation occurs if alpha is large. Inflation occurs when you can decompose, take a first quadratic expansion of this potential, and it gives you exactly the same predictions as quadratic theory, as normal quadratic expansion. So depending on alpha, small alpha, you're here, and you go below the prediction of Starobinsky models here. You can go below the prediction of Stravinsky model. So this is then not a special point here. If alpha is large, then you go all the way back to phi squared model, and you just, well, this is the running parameter, and I'm going to tell you what is the interpretation of this running parameter. You cross all the way from Planck to the bicep and back. Now, if you go to psi smaller than 0, then here we have a real fun, because previously psi equal to 0 was a no-man land. Everybody knew if you take psi smaller than 0, you kill your model just like that. It's just impossible to have any good models of inflation. And suddenly, we found lots of them. So we call them cosmological attractors. And I will try to explain right now what happened there and why we actually like it. So in order to understand what is going on there, just a thesis. What happens there, if you are studying the model in terms of the original variables, which are proper variables for the superconformal theory before you even go to the Planck mass, before you even go to the normal formulation of supergravity. You start there, you see a cutoff. This is something which we are scared, like you have a cutoff, which means that your theory is unpredictive. What we will see is that you have a theory where you have a cutoff, and it makes the theory predictive. So let's see how it goes. First, like a warm-up, you have a theory which does not make any sense. This is a theory with negative coupling to gravity, with negative kinetic terms, so the scalar field, and with this term, okay? So it does not make any sense. It looks like a totally wrong theory because it's a ghost field. But the theory is conformally invariant. You can go to any gauge which changes the value of metric and to change the value of the scalar field. And what happens is that the scalar field does not have any degrees of freedom associated with that. You can just fix it. You can just make it constant. This is what is called conformal compensator. You take it equal to square root of 6, and what you get normal Einstein gravity plus cosmological constant. So this is just like field redefinition. This is just like choosing the gauge, but sometimes it may be useful to live for a while in the theory before you fix the Planck mass, because then you have some symmetries which remain preserved after you fixed it. It is similar to what happened in the theory of Higgs boson. In this theory, you have unitary gauge which present you everything just observable, and you prefer to live with everything that's observable. Once you are in unitary gauge, you're doomed if you want to calculate radiative corrections. So it's better to keep knowledge about the previous prehistory of the model, because it may give you some fresh ideas, and that's what happened. Okay, so here is the next step in the development of this model. So I have here this field which is conformal compensator, wrong kinetic energy. This is normal field. This is chi squared minus phi squared. This is interaction here. Why am I having here all of these strange combinations? Because this is a theory which has symmetry, like there is a symmetry between space and time. This is 011 symmetry of this theory. And everything is symmetric. Matter field and conformal compensator, matter field and conformal compensator. And then I choose the gauge. It's also have this conformal symmetry there. And then this is the symmetry between these. And in this symmetry, it is there is a conformal gauge where you can choose this. Psi squared plus minus phi squared is equal to 6. It's similar to what happens on the light cone there. Okay, so this, we call it rapidity gauge. Everybody who studies special theory of relativity will find lots of analogies between what I'm going to tell you and what you already know. So in this gauge, these fields are represented like that. You can do differently. Results will not depend on how you go to the final result. It's just when you do things like that, what is the final result? This is your Lagrangian. This is the same as it was before, and the same cosmological constant that was before, and the free field here. So the lesson, if we add here weirdly looking invariant term, then it is like a placeholder for the cosmological constant. And you have here, if it is cosmological constant, this is canonically normalized field, no trace of ghosts, nothing wrong with the theory, everything is fine, and we make a third generalization. We put here any coefficient in front of this placeholder for the cosmological constant. When we do so, we continue doing stuff, and what happens here? You have arbitrary function, but not of the original field, but of a hyperbolic tangent of the original field. Now, of course, if you look at arbitrary function of hyperbolic tangent, you can always take an arctangent of tangent and continue doing all you want to do, but this is admittedly a bit ugly. So let's try to do a simple stuff. If you have original theory and you do the things the way which we are doing before, let's try simple. Let's try like quadratic, quartic, whatever. So let's try to take this quadratic function here, quadratic, okay? Then it becomes tangent squared, and then you have, for all normal functions like that, have the same predictions as for the Stravinsky model, independently of whether it is tangent squared, tangent to the fourth. We called it T model because, first of all, the potential is tangent, like looks like a letter T. Second, because it's tangent. Third, because it's like T model for the cars. It's so universal. Nothing depends on which kind of, how this Ford said that you are free to choose the car of any color as long as it is black. So here, what you have, you start with any theory like that, your potential becomes tangent. And here is a long derivation which you do not care to hear about right now, but it is in PDF file. Anybody who wants to see can check that the predictions of all of these theories is the same as in the Stravinsky model, independently of what kind of tangent you have, etc. This looks like continuation of miracles. So let's continue a little bit further. This is the way how you can, by choosing some specific functions, reproduce your Stravinsky model, and not only Stravinsky model, but some related to it models. And now let's continue further. Let's just take, like a natural inflation, let's take sinusoidal potential, but in the original conformal variables. So in the original conformal variables here, at the square root of 6, well, in the original, actually, it would be 1. But then when we fix the Planck mass, it becomes square root of 6. This is the boundary of the moduli space. You cannot go further, because if you go further, you go to the regime of anti-gravity. We don't want to go there. There will be something wrong here. How can you feel that you cannot go there? Well, when you go to the canonical variables for the same theory, this what looks here like a singularity runs to infinity. And this part of the potential does not change. It just look here, well, compressed, because I cannot show the most important part if I don't compress it. It does not change here. But this last part of the branch becomes stretched to infinity, and it acquires universal form independently of what kind of noise I have here. That's an example. I just plot arbitrary potential, whatever I draw by my hand or by my computer. And then after stretching, I have this part and I have this part, and here you have inflation. And the properties of this inflation, predictions of this inflation, are model independent in this class of models, in the sense that I can choose this function f, whatever I want. And I have universal prediction, which is something which we would like, and here again, the proof that it is going to be universal in a leading order in 1 divided by n, where n is 60, pretty good approximation. Okay, so we are here with all of these different models, not only with 2, we have some universality of predictions. We want to have universality, we want to have to say something which other people will, I don't know, trust, I don't know. Ourselves, let's try to continue. Let's study it with 2 models. So these 2 models, they look much fancier. If you have a similar well, invariance here. It will have, well, more fields, great invariance. You draw simplest potential where everything depends on the absolute value. You have this potential. If you have some dependence on how these, variables enter into this universal function, you have potentials looking like that. They're just fantastic. They're playing with them in Mathematica. It's so beautiful. And then when you study their fluxes of fields which enter this basin of attraction, you start here as different fields, two of them. You may start here, you may start here. Independently of where you start, you eventually end up on one of these, in one of these valleys. And then the prediction, everything becomes one-dimensional. You start with two-dimensional picture, everything soon becomes one-dimensional. In one dimensions, we have universality of predictions. So we have these kind of plots where you see how everything zooms into one of these two valleys, and you have the same kind of predictions. You start with chaotic potential, which will scare us, and Liam scared us in particular, because he said, here is this arbitrary random potential in supergravity, never give us anything good. Here is arbitrary potential in supergravity, but yes, but with the condition that this is not in supergravity. This is a more basic theory. This is a starting theory, which is superconformal. If you do chaotic stuff there, only things that are at the boundary matter, and when you plot the potential, it produces you wonderful de Sitter kind of valleys and very non-wonderful anti-de Sitter kind of valleys. So if you are here, you are dead, or you are not even alive. And if you are here, you have inflation with universal predictions, which are, well, just great. Okay? Now, if we change something here, and that is something which we studied later, it's possible to modify the theory a little bit. And in these theories, your cutoff appears not at the universal value square root of 6, but at square root of 6 controlled by some parameter alpha. If you do so, then you have this R, which is proportional to alpha. So then you modify the theory, but for every alpha, you have universality. For every alpha, you can change this value of f, and you have the same kind of predictions. Now, if you start with a theory which is some power of this phi, you have at large alpha. Usually, this universality is at small alpha. But if you start with a theory which looks like power of that at large alpha, then you have the same predictions as in the theory phi to the n, and this is what we have. See, we did not know that bicep is going our way, but we plotted it long time ago. So what happens indeed, for all of these models, we have this attractor point here, which have universal predictions independent of these models. But if we take direction back to large alpha, then you reproduce all of your chaotic inflation models with different values of phi. And, oh, okay. What? Okay, good. 20 minutes for meaning of life. Oops. Okay, sorry, a simple question first. Okay, what is the meaning of alpha? Because meaning of life we can debate, and meaning of alpha is something geometric. You start with supergravity, and what happened, and this is something which Renata discovered, that the curvature of the Kähler manifold is inversely proportional to alpha. Or if you are more accurate about that, because you have some fields there which evolve. This is, your inflaton field. Some fields which do not evolve. So it's called sectional curvature of the Kähler manifold in the interesting direction. And it is inversely proportional to alpha. The meaning, small alpha means high curvature, means small r good for Planck. Large alpha means small curvature, flat manifold, means large r good for bicep. So what does it mean? This means that maybe, and that's being very, very optimistic, if we take this data and we try to interpret, if this class of theories is right, what we are learning when we are looking at the sky, we are learning maybe there is something about non-minimal coupling to gravity, or maybe something about geometry of superspace. And then here is something which came as a surprise to us. Previously, we studied these functions taking simple samples of them, like take the theory phi to the n, well, phi squared, whatever. Now let's take just a combination, which is, well, a series of that. And in normal theory, you can hardly expect any inflation whatsoever. Here, this will be series of tangents, and for all of the theories, in the limit of large alpha, you do have inflation, and the prediction of inflation in this set of series is the same as prediction of the simplest quadratic chaotic inflation model with which I started the discussion. Here is the meaning interpretation of that. This is how potentials look in the original conformal variables. Here is how potential looks in the terms of canonically normalized field. This is how potential looks when I start increasing parameter alpha. So increasing parameter alpha stretched this horizontally. Here, without any stretching, here we do not have any inflation. We have inflation only here. That's why universal prediction. When we go to large alpha limit, we still have inflation falling from this region, but this would be a billion orders of, n equal to a billion. N equals 60 will be near the minimum. And this place, which previously was unsuitable for inflation, will be perfectly suitable, and it's quadratic, and it's quadratic, and it's quadratic. Then you have the same predictions. And this is something which illustrates it. We just run series of different test functions. And what we get, you have a series of, well, connections here. This is a tractor which appears when you run in the direction of small alpha, okay? This is what happens when you take a generic, well, Taylor series expansion and you go in the limit of large alpha, and they all meet in this place of quadratic model. I'm not selling quadratic model. I am not selling Stravinsky model. We're trying to find out what is actually possible in terms of these supergravity models. How can we describe whatever people say us is to be described? So now our conclusions. First of all, it's our deep gratitude to our experimentalist colleagues, because over the years, first of all, they presented ample evidence in favor of inflationary cosmology, and it was independently of anything related to gravitational waves. I personally had sufficiently large confidence believing in inflationary cosmology independently of any data on gravitational waves. I feel that if we have gravitational waves, it will add quite a lot of our understanding. But it was a bit incorrect way of public advertisement saying, this is a smoking gun for inflation. Without smoking gun, we do not have inflation. This was just wrong. This was, well, totally incorrect. Now, this last year was especially exhilarating, nerve-wracking, I don't know. This was one of the most productive periods of my life, because suddenly you have targets changing and you shoot in all directions and you learn in the process. So this was very interesting what we found. In particular, what we have found is the broad class of inflationary models based on supergravity, including the models which we call these cosmological attractors. And these models, the existence of these regimes, as well as other observational consequences, are very stable with respect to deformation of the models that we sell. Take the model, bend it, you still have the same results, which is maybe good. But if you bend them very strongly, then you have two attractor points. And this one attractor point is very low NS plane, another attractor points very high, and that's this dichotomy which we have at this meeting right now. Okay? So on a personal note, how I consider myself, okay, nobody cares, but I care. How I consider myself while waking up every morning, and I found myself in a very interesting position. I just notice it about myself. I am waking up, I am going out of the door, whatever, I am saying something, and I start recognizing what I'm saying incredibly interesting. I was surprised why I'm repeating it. I'm saying incredibly interesting. Next day, I'm repeating myself, incredibly interesting. So that's how I want to finish this talk. Thank you.
So any questions for Andre after that great talk? Yeah.
So another data set of interest is what will happen at the LHC. And so far, although a lot of theorists said supersymmetry, it hasn't happened. But you seem pretty confident that one should work with supergravity. So could you comment a bit on that?
Well, I guess you are pretty confident that superstring theory is going to show us something, even though there are zero evidence in favor of it except for vanishing with the cosmological constant right now. We're trying to build theories, well, to the best of our understanding, which direction controls some bad well, properties of the models under control. And supersymmetry hopefully does it. And superstring theory hopefully does it even better. In string theory, it may be a little bit more difficult to keep control over the supersymmetry. We try to do it manifestly. I do not think that our approach is better than anything else, is better than following string theory directly. We think, however, that these restrictions which we self-imposed on ourselves put us into extremely difficult position when nothing was able to do at all. And now we are finding lots of theories with interesting symmetries. So we think that the possibility to make it in this context just makes us more sure that something beautiful may exist in inflationary theory, even if you self-impose on yourself constraint of supersymmetry.
More questions? Since we have a couple minutes, let me just ask, can you take this opportunity, I mean, with all the data, it's great to match the data with the parameters. What is your current feeling about the more conceptual questions about the anthropic principle, the multiverse, eternal inflation, how that all fits into this?
Okay. I believed into anthropic principle from the very beginning when inflationary theory was proposed. In fact, back in '82, the first thing which I realized about inflation is that if you say that our universe is like we see it right now, say painted blue, whatever, everywhere the same as what Einstein wanted. He wanted to have one theory explaining everything that we see, and he wanted to everything else to be logically impossible, logically inconsistent. That was a dream, that maybe what we will find that only one of the theories would be logically consistent. Then what inflation did, it explained why everything that we see is so uniform, that why it is like that everywhere. So it explained why a person like Einstein could dream of explaining it in a uniform way. And then simultaneously, you just think about the football, okay? Some part of the football is, that's how I explain it to my medical students, okay? So part of the football is white, part of the football, and they are smart. Okay, and they do not want bullshitting. So part of the football is white, part of the football is black. And then you expand it exponentially, and then you leave on the white part, and you try to convince everyone that only white is possible. Then you leave on the black part, and you try to convince everybody and try to construct theories which predict that our universe must be black because this is what I see, okay? And this is just stupid, okay? You like it, you do not like it. Inflation allows you to start with some chaotic distribution of different fields, and then it makes them flat, and you're lucky to live in black, or you're lucky to live in red, and you should not have this monotheistic approach to everything, that you have one God, you have one law, and this must spread all over the universe. Well, I was in the country which had this idea that everything must be red. I came to this country, well, we just have different countries. Our universe can be divided into exponentially large different countries. And string theory allows you to have exponentially large variety of different countries with different properties. Yeah, I think that we have a very interesting, well, lifetime ahead of us studying these possibilities. And I think that this now is the basic hypothesis, not the hypothesis that the universe is uniform. This, the fact that that the universe is uniform, this is something to be proven. And there will be no experimental evidence in it. Because inflation tells you that other parts are so far that you cannot observe them. So depending whether you're an optimist or you're a pessimist, if you're optimist, you say they are so far that you can never observe them, and therefore we are living in the universe. If you're a pessimist, or vice versa, you say that actually you never can disprove the possibility that our universe is multiverse. And if you cannot disprove it, then you have this powerful weapon of thinking about and explaining things around you in an anthropic principle way and saying that God did not create this universe for benefit of a special type of monkey, but some can live in one environment, some can live in another environment, and all of this is equally legitimate.
Other questions? Yeah.
Yeah, just general. How interesting would it be to measure non-Gaussianity or try to characterize non-Gaussianity in this framework? Would it be of any help, or is it hopeless?
Non-Gaussianity is a very powerful sword. If you find non-Gaussianity, it's great. If you find too much of it, it will be bad, but yes, it will be great as well. So we were absolutely, the community of cosmologists were divided into two parts. Half of them were extremely unhappy when Planck have discovered no noticeable Gaussianity. Part of us, including me, were extremely happy when this did not happen because simplest models of inflation, the nicest one, can still work. It does not mean that non-Gaussianity will not be found in future. We have lots of tools prepared to explain whatever happens later. We can do it in supergravity even, okay? So it is possible. And of course, if we find it, then we will learn quite a lot more about inflationary theory. So yeah, we should continue studying it.
Anything else? All right, let's thank Andre again.